Hi everybody. Today I'm going to go over how to derive the fundamental equations of kinematics. So first we will start with the equations, the basic equations of velocity, acceleration, and distance. So V is the velocity. V is equal to ds over dt. This is the instantaneous formula for the velocity. S stands for the position and t is the time, while v is velocity. So this means that velocity is the differential or the derivative of position. If we take another step, that is, if we take another derivative of the distance, we get acceleration. Or if we take the derivative of velocity, we get acceleration, which is A is equal to dv over dt, or the second derivative of position. Now we have v equal to ds over dt and A equal to dv over dt. I'll highlight dt with red and try to calculate for dt, and let's see what we get. So dt is equal to ds over v, and dt here is equal to dv over a. Now we just need to set these two equal to each other. We have ds over v equal to dv over a, or we can write this as a ds equal to v dv. So I'm just going to write the three formulas that we have so far. We have v equal to ds over dt, a equal to dv over dt, and a ds equal to v dv. So in order to get an expression for v, an expression for s, we need to integrate. So we need to integrate this. We also need to integrate this to get an expression for the distance, an expression for the velocity. So I'm just going to number these three, 1, 2, 3. These three formulas. So if we take equation 2, we have a dt equal to dv. So we just need to integrate both sides. Now this is the differential, right? We have the one that has a d, that's the differential. So the limits go, for this one, go from 0 to t. And for this one, they go from v naught, which is the initial velocity, to the final velocity. So if we integrate this, we get a times t minus 0 equal to v minus v naught, which means v is equal to v naught plus at. Now I was allowed to do this step right here, provided that a is constant. If a is not constant, you cannot treat this as a number, as a constant, and take it out of the integral. So this only applies if a is a constant. If I do the same thing for equation 1, I have ds is equal to integral of v dt, and the integral goes from S0 to S. This goes from V or 0 to T. Now here we have dt and also V, but we can't treat V as a constant and put it out of the integral. So what we need to do is plug in this V into this. Then this becomes S minus S naught is equal to integral of 0 to T of V naught plus AT dt. This then becomes V naught T plus 1/2 AT squared. And this is S minus S naught. Or more commonly, S is equal to S naught plus V naught T plus 1/2 AT squared. Again, this only applies if A, or the acceleration, is constant. And now we just need to do the equations 3. For equations 3, we have A ds equal to V dV. Just make sure. A ds equal to V dV. And we integrate again like we did. S naught to S, and this V naught to V. And we have A times S minus S naught equal to V squared over V, going from V naught to V. If we simplify, we get V squared is equal to V naught squared plus 2A S minus S naught. So these are our fundamental kinematic equations. This one, this one, and this one. Now I'm going to go over an example and to see how these formulas are used. So the example says there's this building. This is the ground. And there's this ball that's been dropped from the top of the roof. And there is a window right here. The window is 2 meters long, and the time that the ball takes to go from the top of the window, from this distance, from this position to this position, for the ball to go from here to here, takes 0.4 seconds. T is equal to 0.4 seconds. So now the question is asking the height from the roof to the top of the window. I'm going to call that YR. To solve this problem, we're going to use one of these equations. Primarily, we're going to use the second equation, this equation right here. Y is equal to Y naught plus V naught T plus 1/2 A t squared. This problem deals with a ball falling vertically, and the gravitational constant in this case is gravity, which is equal to 9.81 meters per second. So we can substitute the a for g. So this can be written as y is equal to y naught plus v naught t plus 1/2 gt squared. Another important thing to do at this point is to set the coordinate system. Coordinate system, I'm going to choose y to be downward, positive y, and y equal to 0 is this right here. This is y equal to 0, and it's going downward to be positive. We don't really care about the x position because the ball is just going downward, it's just going vertically, it's not going sideways, so we don't care about the x. So I'm going to use red to signify the region from the top of the window to the bottom of the window. Okay, so I'm going to use this formula right here again. I'm going to write it again. Y is equal to y naught plus v naught t plus 1/2 gt squared. I'm going to write it as y minus y naught is equal to v naught t plus 1/2 gt squared. Y minus y naught, I can write it as delta y is equal to v naught t plus 1/2 t squared. So the red region is the region of the window. Okay, red is region of the window. Delta y is the height of the window, which is 2 meters. We don't know what v naught is. When the ball falls, it has initial velocity at the top of the window and a final velocity at the bottom of the window. Okay, so we don't know what v naught is. T is 0.4 plus 1/2. G is 9.81 and T is 0.4 squared. If we rearrange, V naught is 2 divided by 0.4 minus 1/2 9.81 times 0.4. 5. This is 5 minus 1.96. This gives you 3.04 meters per second. This V naught. Now I'm going to use orange or yellow for the region from the roof to the top of the window. So y is equal to y naught plus v naught t plus 1/2 gt squared. So this t in orange is not the same as the t in red. There's a difference because this orange is from the roof to the top of the window. So the time that the ball takes from the top of the roof to the top of the window is not the same as the time as t equal to 0.4, which is the time that the ball takes to go from the top of the window to the bottom of the window. So there is a difference. So we need to be careful. we need to find what this t is. But we can simplify this formula. Y naught, as we can see here, is 0. Y is 0 when the ball is at the top. So Y naught is 0. V naught is 0 because the ball was dropped. If the problem says the ball is thrown, then it has an initial velocity. But if it is simply dropped, then the initial velocity is 0. So this also simplifies to 0. Y in this case, as I've said here, is YR. So YR is equal to 1/2 GT squared. Now how do we find what T is? Here we're going to use this formula. V is equal to V naught plus GT. Again, this V naught in orange is not the same as the V naught in red, but there is some correlation. There is some correlation that we can use, and that is V final, V in orange here, is the same as V naught in red, right? Because look, think of it. V naught in red is right here at this point, but that is the same as the V final of orange right here. Okay, so I can use this equation or this identity and write it as 0.04 is equal to, we said V naught in orange is 0, so this is 0, is equal to G times T. T then is equal to 0.4 divided by G, which is 9.81, which is equal to, if you do the calculation, is equal to 0.310 seconds. Now that I have this T in orange, I can plug that in to this and solve for YR. Now YR is equal to 1/2, G is 9.81 times T is 0.310 seconds. Squared, excuse me. Then this becomes, your final answer is 0.471 meters. I did not put the units, but if you are doing in an exam or in a homework, it's good to show. I'll just show it here if you want. So YR is equal to 1/2. G we said was meters per second, 9.81 meters per second, and time is 0.310 second squared. So this squared will simplify with that, and then you're just left with meters. So our calculation is correct. So final answer is YR is equal to 0.471 meters. And this is the distance from the roof to the top of the window, which is what we asked. I hope this made sense. If you have any questions, you can ask me in the comments. Thank you.